Okay, in this problem, we have reactions A to B. So A is our product or reactant, and B is our product. In this problem, we want to identify the rate of reaction from the experimental information given in the table. So in this table, we have the time of the reaction is from 0 to 2 seconds. So after at the beginning, where the time is at 0, we have 1 molar concentration of A and 0 molar concentration of B. But after 2 seconds, our A has a molar concentration of 0.98 and our B has a molar concentration of 0.02. And that is because as reaction proceeds, the reactants decreases over time while the product increases. So let's solve for the rate of reaction that is happening in this sample problem. Okay, so what they're asking us is basically, so let's have this as our given. And what they're asking us is the rate of reaction. And if you guys remember your formula that we've just talked about, the formula for rate of reaction is basically, in this case, we'll take A as our reactance, so that's negative 1 over A multiplied by the change in the molar concentration of A divided by the change in time. And in this case, we have B is our product, so that should be positive. So 1 over B multiplied by the delta molar concentration B, or the change in the molar concentration of B, and the change in time. So let's do our solution. So in this problem, we can calculate the molar or the rate of reaction by either solving for the rate of A or the rate of B, because they should be equal anyway. So in this case, we know, or let's solve for A. We know that A is our reactant. So if we follow this equation right here for A, we will get 1 over A. But since we don't have any coefficient for A, so that's basically 1. So that is 1 multiplied by the delta change in A. The molar concentration of A is, the final is 0.98 minus 1 divided by the delta change in time. T final is 2, T initial is 0. So the rate for reaction A is equals to negative, that's 0.02 molar concentration divided by 2 minus 0 is 2 seconds. And that gives us a rate of 0.01 molar per seconds. And that should be equal to the rate of B, because there's only one product and there's only one reactant. So for B, so the rate for B is equals to 1 over B. In this case, there's no coefficient for B, so that's basically 1, and it's positive because it's the product. And then we have the delta change in B, which is equals to, our delta final is 0.02 minus delta in molar, initial molar is 0.00 divided by delta final time is 2, initial time is 0. So the rate for B is actually equal to positive 0.02 positive 0.02, right, 0.02 molar divided by 2 seconds. And the rate is equal to, oh, this should be negative, sorry. This, I got confused, they're both positive. This should be negative because 0.98 minus one is negative 0.02. Negative and negative, that gives you positive. So the rate in the end should be equal to 0.01 molar per second. So they're both equal in rate. So that's how you solve for rate of a problem. Let's try this example. We go back to the chemical equation that we had earlier. So we have 2 moles of N2O5 in gas state as our reactant, and it decomposes to 4 moles of NO2 in gas and 1 mole of oxygen gas. If O2 is formed at a rate of 9.0 times 10 raised to negative 6 moles per second, A, find the rate of formation of NO2. B, find the rate of disappearance for N2O5. And C, find the rate of reaction. So what we were given is we are given the rate of formation of O2, which is equals to 9.0 times 10 raised to negative 6 molars per second. Moreover, what are they asking us is from this rate of formation of oxygen gas, we want to first find the rate of formation of NO2. Formation, it's because it's the product. We're forming the product. B, we want to find the rate of disappearance of N2O5. So it's disappearing because it's the reactant. And C, what is the rate of the overall reaction? Rate of reaction. Okay, so the formula that we're going to use is the formula that we just talked about. In this case, so let's apply this. So we have our A as our reactant, B and C as our product. This is our reactant. So that should be a negative for A, which is 1 over its coefficient. It changes in its molar concentration divided by the change in time. And that should be equal to 1 over B. This is positive. This is because it's a reactant. It's forming divided by delta T. And that should be equal to 1 over C, change in the molar concentration of C over a period of time. Okay, so let's go for the solution. Okay, so first we want to find the rate of reaction for N2O or NO2. Okay, so we can use the rate of the formation of O2, C, to find the rate of formation of our B. So what we're going to do is use the equation 1 over B, change in the molar concentration of, this time we're doing NO2. We know, well, let's just write it first. Okay, and then let's look at the equation. So we know the coefficient of B, we have 4 moles, so that would give us 1 over 4 multiplied by the change in the concentration of NO2 divided by delta time. And for C, we have 1, so that leaves us 1 over 1, that's 1. And the rate of the change of formation of O2 is 9.0 times 10 raised to negative 6 molars per second. So are we going to solve this? We just have to multiply both sides by 4. So cancel the 4. The reason with that is because from this equation we know that as 1 mole of oxygen is formed, there's 4 moles of NO2 being formed. So NO2 is forming 4 times faster than O2. So in this case, so this is the rate of O2. If NO2 forms four times faster, we just have to multiply this by 4. So the rate of NO2 delta, the change in the rate or the change in the molar concentration, which is the rate of formation, is equals to 9.0 times 10 raised to negative 6 molars per second times 4. That is equal to 3.6 times 10 raised to negative 5 molars per second. And we can also do the same for how we can find the rate of disappearance for N2O5. We use the same equation, but this time look, we have 2, and you can either use this now or use this. It doesn't matter, you will get the same answer. But let's use oxygen. So 1, since this is our reactant, that's the negative 1 over its molar coefficient, which is 2, and the change in the molar concentration of N2O5 divided by delta T is equals to, again, we only have 1 here, so let's write that. And the rate of formation of O2 is 9.0 times 10 raised to negative 6 molar per second. And as you can see here, as the reaction happens, as 1 mole of oxygen is being formed from 2 moles of N2O5 disappears. So what that means is that N2O5 disappears twice faster, 2 times faster than O2 is appearing. So from here, we just have to multiply both sides by 2 to cancel that. So that would lead us to, we have to multiply them by negative to negative, because we want to have this as negative because N2O5 is disappearing. So the change in the molar concentration of N2O5 is equals to delta T is equals to 9 times 10 raised to negative 6 multiplied by negative 2. And that would give us the rate of the disappearance of N2O5 is actually equal to negative 1.8 times 10 raised to negative 5 molars per second. So that is the changes of disappearance, the rate of disappearance of N2O5. As for letter C now, we can use this equation to solve for letter C to find the rate for letter C. So what we just have to do is substitute the value. We have negative 1 over 2 multiplied by negative 1.8 times 10 raised to negative 5, and that is equal to the rate of the formation of NO2 is 3.6, but we have 4, so formation 1 over 4 multiplied by 3 times 6, or 3.6 times 10 raised to negative 5 molars per second, and that is equals to 9.0 times 10 raised to negative 6 moles per second. So if you solve this equation, all of them will come out in the same value, which is 9.0 times 10 raised to negative 6 molars per second. And as you can see, it is equal to the rate of the formation of O2. That is because the rate of formation is basically equals to the rate of the formation of 1 mole of an element or atom in the reaction. So for C, the answer is equal to the rate of the formation of oxygen, which is 9.0 times 10 raised to negative 6 molars per second. So that's how we use and solve for the rate of reaction, for the rate of reaction. Now let's talk about some things that affects the rate of reaction. So what makes this rate to go faster or even slower? But most of the time we're dealing with how can we affect the reaction rates. So there's 4 things that can affect the reaction rate. One of them is the concentration of reactant. Number two is surface area. Number three is temperature. And number four is catalyst. So let's begin with the reactant concentration. Um, in theory, in increasing the rates of reaction by increasing the speed of the reaction, what we need to do is actually to increase the concentration of reactants. So we're dealing with reactants here. By increasing the rates or increasing the concentration of the reactants, so increase concentration of the reactant, the rate increases. You have an increase in rate. That is the concept. So remember that increase in the concentration of reactants, smaller concentration of reactants is equals to increase in rate. Another thing that affects the reaction rate is the surface area. By increasing the surface area of one of the reactants, so increased surface, let's write on top. So increased surface area is equals to increase in the rate of reaction. So let's talk about how does that happen. Okay, so let's take this as an example. So we have zinc solids and we introduce it to 2 moles of HCl, which is aqueous, and the reaction forms a gas hydrogen. So let's just focus on the formation of gas hydrogen between these two reactants. So if we have a beaker of HCl and we introduced a zinc solid. So this is our zinc solid. Bubbles will form, and those bubbles are actually the H gas, the hydrogen gas. Okay, so that is what is happening in this reaction. So if let's say if we have 3 moles of HCl and we want to increase that mole, so let's increase the mole. Instead of having 3, we increase the mole into 6 moles of HCl. And we have that same zinc solid. What will happen is you would actually have an increased release of hydrogen bubbles. So here you have 5, here you have much more. We don't know how much, but we can compute that. But we're not gonna do so. We're just studying the theory anyway. But the theory is, as we increase the concentration of one of the reactants, in this case we increase the concentration of HCl from 3 to 6, the rate should actually increase. Okay, so increase in the molar concentration of reactant, the rate increases. So as you can see here, the form bubbles increases. As for the surface area, so let's say we have again the beaker. And in this beaker, let's go back to our 3 moles of HCl. And then let's go back to our block of zinc solid. And we know that a certain amount of hydrogen bubbles should be formed, so in gas form. But let's say we change this situation. Instead of using a block of hydrogen or zinc solid, we use pieces. So we grinded it. We took it into smaller pieces of zinc solids. What will happen is you will actually have an increase in the release of hydrogen. And even if the molar concentration of your HCl is still the same. So even if this is still 3 moles of HCl, but you would have an increase in the release of hydrogen gas. That is because the zinc solids are now has an increased surface area. So what is happening here? Why does the product increase if we increase the reactant, the concentration of the reactant, or increase the surface area of one of the reactant? Let's go back to the bumping scenario. So we know that in chemistry, reaction is basically atoms bumping. By increasing the molar concentration of HCl here, we have more molecules of HCl bumping onto this block of zinc solid, and more bumping of that HCl molecules will increase the production of hydrogen gas. The same thing here, after grinding it, we actually increase the surface of the zinc solid. There's more area for the 3 moles of HCl to bump onto this zinc solid. The reason that it has less here when it is bigger is because it's only bumping on the outer surface. So the zinc solid inside, the one that is not exposed to HCl, is not being targeted, is not being bumped by HCl. But after you grinded it, you have more surface area exposed to the 3 molar concentration of HCl, so there's more bubbles of gases released. So both increases the rate of reaction. Now let's talk about temperature. Temperature is easy to understand because chemical reactions typically occur at higher temperature. Um, for the main reason with that is because again, atomic reaction is basically bumping of atoms, and that is related to their kinetic movement. So the faster the atoms move, the higher the chance and the probability of them bumping, and the stronger the bump. So increasing their kinetic energy would actually also increase the probability of bumping onto the different molecules, and not only bumping at a higher speed, but also more chances of bumping at the appropriate orientation, and that will result in increased reaction rate. Simple as that. And lastly, catalyst is basically a substance that is used in the reaction that is not consumed but lowers the activation energy for the reaction to start. So activation energy is a concept that is required for the atoms to reach before a reaction is formed. Remember, going back to that scenario, as the atoms bump, also a lot of the bumping that is happening on the reactants does not immediately result in a chemical reaction. What needs to happen is, I've mentioned this, is that the bump needs to be hard enough, and then the bump should be in the proper orientation. And let's focus on the bumping hard enough. If the two atoms bump together really hard enough, so they bump really hard enough, they will create this activation energy. They will reach this activation energy, and after reaching that, the reaction will proceed. And a lot of the reaction that is happening has sometimes requires a very high activation energy to reach. So what you want to do is you add a catalyst, and the catalyst lowers that requirement of activation energy for the reaction to proceed. So let's take this an example. We have hydrogen peroxide. 2 moles of hydrogen peroxide, H2O2, actually decomposes to 2 moles of H2O and 1 mole of oxygen atom. What this is hydrogen peroxide. If you guys have heard of peroxide, it's usually used for wound cleaning, and it is actually always decomposing. The reason that it is just not visible in the decomposition, it's because it's decomposing very, very slow. The way that we can increase the decomposition is by adding potassium iodide. Potassium iodide will accelerate the decomposition and will accelerate the rate of reaction by lowering the activation energy. So the iodide ion will jumpstart the reaction, and it will make the reaction go faster. Here's an example right here. So if I have hydrogen peroxide and then an added Ki, the production of water and oxygen will increase. But the Ki is not consumed because it's just act as a catalyst. So here's an example. So what happens is that, so if I add Ki, so for example, I have Ki here, and I have hydrogen peroxide here. If I include those two together, or let's just say if we added just H2O2, hydrogen peroxide, it just remains hydrogen peroxide. You will not see the production of water and oxygen. But if I added Ki, you can see here the production of oxygen and water trapped in the soapy snake bubble. And we just added soap. So if I have H2O2 with soap, I just put it there. We just have a soapy H2O2. But if I added Ki, H2, water and oxygen will be released, and those gases, especially oxygen, will be trapped into the bubbles from the soap, creating this kind of like this plume of soapy snake here. So that's what catalysts do. They speed up the reaction. So remove the Ki here. You just see a very slow decomposition of hydrogen peroxide. So that is what's all about rate of reaction. In our next lesson, we're going to continue on, and we're going to be discussing the order of the rate of reaction and how to create formulas on how to solve for the rate of reaction. If you guys have any questions about the lesson, please message me and have a good day.